All right, so let us begin. Yeah, so you will slowly come to know through, within, I think, 2 weeks, what is computational nonlinear dynamics. What is computational here in this course? What computational thing we will do? Wow, what is nonlinear here? And what is dynamics here? So each of the component you will slowly get to know in the upcoming weeks. The background is very nice, and it is a computer generated plot. Okay, it's generated by one of my systems, and basically you will come to know what this is. This is basically a 2-parameter diagram. Okay, so it's a bit involved, like what this color means, why it looks like a yacht. What shape do you think it looks like? What's the shape of these? What common shape do you see in each of these colors? So there was a scientist named Arnold, and he gave this name as tongs. They appear like tongs to him. Okay, if you invert them upside down, it will look like a tong. Okay, so you take your tongue out and just see in your mirror. It will look like that. Okay. So it's a very nice concept, and the main beautiful thing is if you keep on zooming, if you can see here, let me turn on this one. Yeah, if you see these things, no, if you see, sorry, like, see, this is the bigger part, isn't it? But if you see in between these two, there is also a dot. Okay, in between there is a dot. In between this and this, if you zoom in this one, so it is deep inside. How much ever you go zoom in, similar kind of structures appears. Any scale you take, any scale. So how much it depends on your computational power. 10 to the power minus 20, 30. How much computer is able to take the decimal? Okay, and the math behind it suggests that it will go infinitely. How much you can go? 10 to the power minus 100, 10 to the power minus 1000. Anytime, even the computer cannot do. It is still there. Okay, that's what this self-similarity means. This self-similarity means like this is a fractal. Okay, fractal is a self-similarity thing. It is self-similar across all dimensions. Okay, so self-similar, if you see like broccoli is a good example. If you take a big broccoli and then take a small part of that broccoli, then zoom it in, okay, and take a photo and send it to your friend and ask him, is this a broccoli you want? He will say yes. And then you take that small broccoli and give. Then you'll say, why have you given this small broccoli to me? Okay, then you say, yeah, it appeared look big to me, It's a small copy of that. So the small copy looked like a big one when you zoom in, okay? So that's what is known as a fractal. It is self-similar, okay? So first of all, in this course, we will learn about discrete maps. Like over the years, if you take weight versus year, okay? This year you enjoyed a lot, weight has increased. Next year you went on a diet, weight has decreased. Same, how it varies over time. But if you see the year count is changing by +1, okay? 2021, 2022, 20. It changes discretely by a discrete amount of 1 year. Step is 1 year. Okay. So therefore, this is a discrete map. Okay, this is a discrete map, and it is a very simple case of a dynamical system, how it changes over time. So therefore, that's the simple case first we will encounter in the course. Discrete map. Now, discrete map can have a lot of different versions. One dimension. Okay. Say we are telling only population over the year. Okay. How about population and weight over the year? If you take population, maybe population of okay, population of Akul and weight of Akul over the period of 30 years. Okay, over the period of 30 years. So the data you will get. Okay, so now, but the data will be two-dimensional. Why? The okay. Yes, I did not thought about it. Okay. The weight and population, these are the two parameters and keeps on changing. So it's two dimension. If I take only the weight, it is one dimension. If we say like population, weight, and number of friends, okay, that's three dimensions. So there are one dimensional map, two dimensional map, three dimensional maps. Okay. Now that discrete map is done, that we will see as a first part of the course. Second part of the course will be on differential equations. Okay. In the sense that you don't solve it on paper. Since it is non-linear, it is very hard to solve it on paper. But what we will solve here is first we will look into a linear ODE. X dot equals to AX, dx by dt equals to AX. Okay. If A is greater than 0, then you know it is exponentially increasing. That we will see. So those kind of linear, just class 12th differential equation bit will be used, but not too much. Just to give you an idea, how complex nonlinear is. So in order to understand how complex the nonlinear are, we have to see the simplest case first, that is linear ODE. That's the motivation why we will be learning a bit about linear ODE from population dynamics perspective or any other applied perspective. Okay, then suddenly see a drastic change happening when you take nonlinear ODEs. Okay, so that will be our main idea over there. Maybe we'll go to 2D and systems we will take into consideration. The main aim of the course is to make you aware that some very simple nonlinear systems can exhibit striking complicated dynamics, which is not usually covered in your master courses or any of the engineering courses around you. So that's the main motivation of this course, to make you understand about this field, to make you aware of this field exist. Okay. And the third part of the course, I think, will be fractals. Okay. So I will give you a very nice example just now. So, all right. So, yes, chaos theory was actually first got revolutionized by Edward Lorenz. Okay, by Edward Lorenz. He was basically a meteorologist at MIT. Okay, and what he did, he predicted weather systems like based on the data observations he was getting. And inside you can see his picture, Edward Lawrence, and on the left you see his supercomputer. At that time, around 1960s, he named it. I think his the name is Royal Magby. Okay, if you read this book, there it is mentioned about his supercomputer, Royal Magby. What he do is he just gets the data from the weather data from different physical measurements like temperature things, temperature, precipitation, all those, and he feeds into his model, which he has written a computer program for it. Okay, and those data, input data you feed, that will give you the output. What is the output? How the weather will look like tomorrow. Okay, or maybe after 2-3 days. So what he did, when he gets this weather data, okay, the weather data will be just numbers, isn't 0.2 degrees. 15.2 degrees means, will it be exactly 15.2? No, it will be 15.115893 like this, a long decimal place. So and he was, I think, hungry. Okay, one day in his work he was hungry, so he wanted to put input and go for lunch, so that by the time he comes after lunch, the program would have given the output and he would be ready to make the. Okay, so what he did is he got, I think he truncated some of the decimal places. Instead of 15.8965, he took 15.3839. Okay, because 389 he did 39. Okay, so and he fed the into the model and started computation. And in his time, the computation takes around lot of hours, like 3-4 hours. Okay, and by the time he came from lunch, he took the data. Okay, then what he found? He found that his weather prediction data shows flood. Okay, today was a good weather, but after 2-3 days it is showing flood. Okay, so he was surprised because he went into an alarm mode that why my program is showing flood. Why my program is showing flood? Because even if today is a good day, like a good weather, so he actually thought the program is wrong. So he double checked, he debugged his code, everything he tried, but he could not find. Okay. Then he later realized that the input he fed was truncated. So what he did is he used long decimal places in input again, the original set of data, and again ran the simulations. Okay. Then he found it is giving accurate results of similar results like today. Okay. So then he saw that these two different initial conditions, but just by varying in decimal places, like a small change in initial conditions, were leading to huge change in output. So this, like he got very much enthusiastic about it. And what he did, he started saying about this to different other scientists in the field, but he was ignored. Not many were believing him, not many believed in him. So what he did, so after 2 years, he thought of writing a paper, and he wrote a paper. Okay, a research paper at that time was very prestigious. Okay, so he wrote a research paper on deterministic non-periodic flow. Okay, and on the right you see here it's a model he created based on the weather system. Based on the weather system, he created a model, and this is a just a differential equation. We will come into this later in the course because weather is not discrete. Okay, whether you have, because there is a mixing of air continuously over time, velocity is there, wind velocity, all those things, mixing of different precipitations and all. So it's a continuous time system, like ordinary differential equation system. And he took all this into model, and then he found this complicated behavior. It's like a butterfly. Okay, how if you start from here, this black point, you go like this, follow my cursor, and then you come to the next loop. Okay, and then go to the next loop, and this is a few iteration. But if you do a lot of other iteration, it will create a very complex looking butterfly. I think those who have had numerical method course last time in the last semester, Shankamesh and his group presented about it as a project. Okay, so this is a butterfly, and this resembles a butterfly, but it's a Lorentz attractor. Okay, it's an attractor because any initial conditions will go into. So he gave a talk. Does the flap of a butterfly wings in Brazil set off a tornado in Texas? What does it mean? Brazil and Texas are very far apart, but a small change in the butterfly wings in Brazil, like a small change in initial condition, is bringing a huge change, like a climatic change in Texas. A small change in a flap of wings in Brazil is causing a large change in Texas, a huge weather event. So small changes in initial conditions or initial sensitivity to initial conditions, okay, brings a huge output difference. That is what is known as chaos. It's not chaos. It's not chaos. Okay? It's chaos. Okay. How you will spell it? Yes. You spell it like K-A-O-S. Okay. Chaos. So this is why and you cannot. Can you exactly measure 1 centimeter? No. You can measure 0.99999. You cannot measure exactly 1 centimeter. So every time there is an error for sure. In any numerical computation, any measurements, there is error for sure. You can't avoid the error. And since you can't avoid the error, therefore chaos theory will always persist. Okay, because small error is there. Every time small error will outcome, and you can't avoid the error at all in this scenario, at least in our lifetime. So therefore chaos theory will always be there. Therefore, till now, weather patterns are difficult to predict. Till now, weather patterns in today's age, you can't predict the weather pattern after 2 weeks. Okay, it's still difficult. Maybe in his time, in Lawrence time, a few days was there. You can't predict weather in few days in advance. Due to computational power and all those things, it now the prediction time increased to 2 weeks. Okay, but it's there. We can't predict exactly after that. So this is one very nice example of nonlinear dynamics applied to weather systems or meteorology. You can tell to your geoinformatics friends about this application. Okay. And this is one such example we saw last time, how in Jurassic Park movie, like Ian was explaining butterfly effect to Ellie. Okay, so we won't see the video again today. See it at home. Okay. So we have a couple of examples of chaos. Okay. So we will just see this now. Okay, so one example is this ball you can see, you have a circular boundary, okay, and a ball is released from a center. Maybe later, like we can refresh this one. The idea is two balls are released from a very tiny change in initial conditions, okay. And you see, yeah, these two, there are two balls actually, and they are very close to each other. Now you see, even they started very close to each other, the two trajectories for them are totally different. One is in blue and another is in orange. Okay, you can see light orange. One is in light orange here and one is dark blue over here. And there are two balls, but both of them started from the same initial condition, almost same. Even though you say you can't say it's same initial condition because there is an error associated with the position every time. 0.1, 0. If you say 0.1, the other will be at least 0.1. Okay. So that 0.001 error can cause this huge difference in outcomes. And that is what this nonlinear dynamics is. The evolution of this is nonlinear. Okay. This is one example, bouncing balls in a circle. Okay. Um, what happened here? Can I restart this? Yes, you can see there are 4 or 5 pendulums starting from this very same initial conditions, and you can see how, okay, and you can see they are totally different. Okay, the trajectories are totally different. So that's how it is sensitive to initial conditions, and yeah, double pendulum is one among them. Single pendulum is not chaotic, but double pendulum is. Okay, you can see how it is. You can make a scene that in Avengers movie there you must have seen this pendulum, but at that time you did not recognize theory and chaotic pendulum. Okay, so the pendulum, just he was talking with Potts, and he was having this pendulum in front of him. So it is basically like a version of a double pendulum. It's chaotic. Okay, it's good in the movie that they are appreciating chaos. Okay. So you can now appreciate that this is indeed a double pendulum, isn't it? There is one bar and another bar connected to it. So it's like a double pendulum. Okay. One more example is this Bellows of Jablonski reaction, where you see this chemical reaction happening on a Petri dish. Okay, bio students, you can keep this in mind. So you see this spiral wave patterns forming over here. Okay. So these are the target waves you see over here. They are actually spirals. If you see this center is moving like this, and but these are target waves. These are like the center of the circles are spreading, but here it is a spiral. So yeah, so here it's a spiral, like spiral like structures, and there are many of them, multi-spiral structures. So I think like Jaydev is working on one project on this. So already, and it's with Andre who just messaged. So we kind of do the simulations for this, and yeah, this one such example. In the course, I will show what the project, like the students are working on this, basically simulations. Okay. And chaotic, like chaos theory is not only in simulations or any in just computers and just in mechanical systems or in metrology. It can also happen in electronic circuits. Okay. Like you take a circuit board and just put some, here we have, it's a good classroom. Now I see we are in a perfect classroom. It was meant to be here. Because if you see these guys, there are transistors, there is LED, there is capacitor, there is diode. Okay. And there is on the top left, there is resistors also. All the mathematical operations you see, that is multiplication, can be performed by op-amp, operational amplifiers, and all the other activities like addition, integrated circuits. Differentiation is the opposite element for that. So whatever mathematical operations you carry out in your notebook can be implemented in terms of electronic circuits. Okay. So whatever dynamical systems we will see in this course has a electronic circuit for it. And that's how beautiful it is. That's how beautiful it is, because it's just not in your notebook to experimentally verify whether you are actually seeing this in real life. Okay. You can take it and make it. There are increasingly popular free source simulators known as P simulator, PSIM, PSpice, and also I think MATLAB has this Simulink. So all these softwares are there, which if you just give the dynamical system, they can give you an equivalent circuit for it. You don't have to put lot of knowledge. So therefore, electronics, like if you see in our field, in my field of nonlinear dynamics and chaos, um, much of the researchers are from a background with physics, biology, psychology, neuroscience, and also maybe maths. Yes, mathematics. But recently, since 10 years, if you go to different universities, I was surprised that over India, it's increasingly getting popular. Nowadays, people in electronic engineering, a professor is doing research in nonlinear dynamics. So it's really good. And this is one such motivation for you. So he is Professor Sprott. He is a very well-known scientist and researcher in nonlinear dynamics and chaos from Wisconsin University in USA. And he does basically chaotic systems. Like you will see what I mean by this. Like he takes a lot of different systems and models and try to simulate it in a computer. And later he realized that he can introduce it in electronic circuits. And this is the video about it. Because the brain is like can also occur in electric. And we have electric circuit as an extraordinary. This is a very simple electric circuit. It has only two components. There's something that we call an inductor or a
And then something that we call a diode plant. And with just those two things, we can produce chaos. Because at the input of the circuit, we make a sine wave, a light sine wave we showed over there. And at the output comes chaos. And it's truly amazing that circuits do this. And in fact, we can also explore the transition from periodic
This is a CRO actually, CRO, oscilloscope. You can hear a sound, isn't it? Yeah, so this was one of the examples for the yeah, this is one of the examples where you see chaotic motion in real applications. So as in the last he told, I don't know if you have heard him properly, chaos is very nice in music. That what it makes music in your ears sound good to you. Okay, if it is predictable, it won't be interesting to you. if it is unpredictable, like suddenly the tone gets high, suddenly the tone gets low, and you don't know what is going to come ahead. So for the first time you hear a new music, it's what it makes it more nicer. Okay. So predictability, unpredictability makes everything good. Anyway, these are the videos, and also in solar systems, the moon of Pluto is chaotic. It behaves chaotically, sensitive to initial condition, mostly due to its shape. Okay. And this is the last class we saw about dynamical systems. Okay. So you can see here, like these are systems evolving over time. Okay. I will just go through this quickly. And you can see some examples like motion of planets is a dynamical system. Okay. Your lifetime is a dynamical system. Like infancy, t equals to 0. Then your child is around t equals to 8 years. Then you go to adolescence, t equal to 13 years, so on, and old age. And yeah, that's the dynamical system. How with time the state of your uh, body changes. Okay. And also your behavior in hostels, like this is the hostel H. Okay. Then you move to the mess. Okay. Then to academic office, all the classes are over, you head on to restaurant. Okay. Then you come back to the hostel. Okay. So this is like a dynamical system where you go, it's like a periodic behavior. Okay. Because you always go to the hostel room and to your same room again. Okay. I don't think any other. So you go to the same room again. So it's like a periodic behavior. Every time you start from that room, end at that room, at the end of the room. Dynamical systems can be classified into two types, as you can see here. One is the flow, okay, one is the flow, and another is the maps. Okay. What are flows? Flows are anything which changes over time continuously. Okay. So therefore, these are modeled using differential equations. Like for example, x is a variable which changes over time. And how it changes over time, say dx by dt equals to ax. I am saying here that the rate of change of x is proportional to x, okay, to the state x, okay, depending on the value of a, whether a is positive or a is negative, or a is solution for x or the behavior of x will change, isn't it? So you can just solve this. What is x? Can you solve this? What is x? Okay, just tell me in the next class. Maybe those who are from different, like bio AI and CSDA, and also informatics. Okay, informatics, they can tell me about this. What is x? Depending on what happens if a greater than 0, what happens a less than 0, what happens if a equal to 0. Okay, just try to understand what is going on. So since this a controls the behavior of the dynamical system, therefore it is known as a parameter. It's just like AC in your room. If you increase the AC, temperature decreases. If you decrease it, temperature increases. The same. If you make a less than 0, greater than 0, less than 0. Okay. Now we come to maps. What are maps? So maps are the discrete version of the system. Okay. These are known as recurrence relation. What are recurrence relation? It is of this form: xn plus 1 equals to f of xn. Okay. What is it? Xn is a state now. Say my Akul's weight this year. What's Akul says this weight this year? Maybe 90. Okay. So maybe take. Okay. So so based on this year's age, that is xn is 90, and you predict what is the Akul's age next year. That is xn plus 1. Okay. So future state is being predicted from the past state. Xn plus 1 is the future. You are predicting it from the past xn based on the rule f. F is your rule. Okay. So this kind of relation are known as maps, and these are also known as discrete systems, because this here time is discrete, but here time is continuous. Okay. These are the two models. We will look into this So yeah, these are the things. Furthermore, you can have dynamical systems into two parts. You like linear system and nonlinear systems. Okay. Like linear system, if you see x dot equals to ax is a linear system. Why? Everything is linear here. Okay, but this is a linear system, but x dot equals to ax minus ax cube, it's a nonlinear system because the nonlinear term cube is coming in. So this is a nonlinear system, isn't it? X dot equal to ax, this is a linear system. Linear in the sense it depends on x to the power of 1. But here on the second case, x dot is ax minus ax cube. Okay, here you can see linear is there, but it is dominated by this cube term. Okay, therefore it is non-linear. Got this? Yeah. So therefore there are linear and non-linear dynamical systems. Okay, and these are differential equation. Hence these are known as flows. Okay, flows. Okay, but if you see map, can you give me a linear map? Can you give me an example of a linear map? Halima, maybe. Can you give me an example of a linear map? Linear map, it is simple. See, this is an example of linear system. X dot equal to ax. Yes. So how the maybe the linear map will look like? Simple, maybe axn, just like that. So there is no power involved here. No, power is 1 to the power 1. So can you say give me an example of this is linear map? Can you give me an example of a non-linear map? Yes. Wow. Yeah. This is also a non-linear map. Okay. This is a non-linear map. Okay. So therefore, we are interested in how this x changes over the time. The time series we are interested in. That's it. We are interested in the time series, how this variable x moves in the as n progresses, as different number of iteration increases. Okay. So this is the example we will cover after the break. Okay. Anyway, you can take a break now. We will next class. No, sorry, the next after the break we will start with a computational exercise. Okay, so make sure Python everything is there and started.